Yeah, I'll start. So I'm starting in 3, 2, 1. Say? Hmm? Yeah, I'll start. Yeah. So yeah, welcome everyone for the sixth talk in the Introduction to Cosmology series. So this time we are progressing a little further into the concepts of cosmology by covering the very most intriguing and interesting concept, perhaps the most interesting concept. That is because many people don't exactly know what and how this basically alters our understanding of the universe. So today we're going to cover what we know about dark matter. So dark matter, as people you would have come across if you are into reading science, pop science articles and stuff. So it was actually discovered by Zwicky. So he excuse. So it was discovered by him, and ever since then, we cosmologists have been trying to understand its true nature, as it is really hard to detect a party or an object of which falls under the category of dark matter, as it does not absorb or emit any sort of electromagnetic radiation, and the only way we can know its existence or its influence in our universe is only by observing its gravitational effects on the objects around it. So we will be looking first at let's try to understand what we know from our visible understanding of our understanding of the visible parts of the universe, so that we know that there is something else that we are not able to see or comprehend, that is there, which is altering the nature of space time that we had earlier comprehended. So we know that when we first talk about space and observables, our first thought goes into stars, galaxies, clusters, supernovae, and so on. So stars, as we know, it emit it by the process of nuclear fusion that happens by the reaction in the atom elements in its core. So it emits all radiations of all wavelengths. So it has ultraviolet, it has infrared, visible, and so on. So let us try to first, because there are many kinds of stars as we have seen previously. So let us constrain our condition to the one of our own galaxies, that is the sun. So let us try to observe the sun in the B band. The B band is nothing but the blue filter that is used, that only allows blue and a little bit of violet, violet light from the electromagnetic spectrum. So the sun's luminosity when observed using the B band is about 4.7 into 10 to the power 25 watts. So, so in the B band, the total new luminosity density of stars within a few hundred megaparseconds of our galaxy is about 1.2 in 10 to the power 8 times the luminosity of the sun in B band spectrum, per cubic megaparsecond. So why are we first calculating the luminosity density? So we are very much familiar, like how we use the E by M ratio in the case of electrons and other particles in order to determine its characteristics. So in cosmology, we use this density in order to compute its exact mass and the average mass. I'm sorry. So we use it to compute its average mass and average luminosity, or it's called as the mass by luminosity ratio. So so to convert the luminosity density into mass density, we need to know the mass to light ratio for the stars. So we can see, so the mass to light ratio is for say our sun, because our sun is considered to have a mass of one solar mass, right? So that's about, so the mass to luminosity ratio for our average mass to luminosity ratio for our sun is about one solar mass per the luminosity density the luminosity of our sun in the B band spectrum. So for the this is in the case of the sun. So for main sequence stars, so we know there are from the from the the spectral classification of stars, we know there are many stars, kinds of stars that are present, like the main sequence, red giants, and like red dwarfs, and so on. So for the main, we are considering here the main sequence stars, so which is powered by hydrogen fusion in its centers. So the mass to light ratio for that for main sequence stars, it ranges from a value. So we cannot, since it's an it's an average, we can approximately calculate. So it ranges from m by the mass to luminosity ratio of 10 to the power minus 3 times the mass to luminosity ratio of our sun in the B band for the brightest and the most massive stars to the 10 to the power 3 times our sun's mass to luminosity ratio. So this is in the case of observing the stars in order to come to a general consensus of the average mass to luminosity ratio through which we can understand the characteristics of the specimen or in whatever case. So the mass to light ratio of the stars in a galaxy depends upon the mix of stars it contains. As I've said before, in the spectral classification of stars, we have different kinds of stars that are present. So so we can because they all have sort of different characteristics, as we have seen here. For the main sequence stars, it ranges from this 10 to the power minus 3 to 10 to the power 3 times the mass to luminosity ratio of our sun. So for different varieties of stars in the spectral classification, they have. So we cannot come get into a specific value, so we just take a mix of stars and calculate its average value that we can see from this equation number 3. So within 1 kilo parsecond of the sun, the mass to light ratio of the stars, it works out to be like this. Again, it indicates that we're taking the average value here. So that's about like 4 times the mass to luminosity ratio of our sun in the B band. That's approximately 170,000 kilogram per watt square. So, this is actually, it might prove to be enough. This energy's value, like 170 kilograms per watt square, it proves to be a really inefficient value. But once we try to understand like how exactly bright is the luminosity that we can observe in this certain distance, it's actually really interesting to look at. So if the mass to light ratio of the stars within a kiloparsecond is not unusually high or low, so we are trying to get into the range of homogeneity, the sense of homogeneity in because at such a greater distance, we can almost approximate the mass to light ratio of stars to be uniform, not unusually high or low in the case of different stars that are present in that certain distance. So the mass density of stars in the universe, because this rho is about mass density of stars in the universe sums up to be again this the m by lb ratio of the flux. I mean the luminosity density of the stars. That approximates about 5 into 10 to the power 8 times the solar mass. So the mass density of the stars, 5 to the power 8, 10 to the power 8 solar masses per megaparsecond cube. Excuse me. And yeah, so well, I think we have covered in the previous lectures about the critical density of the universe. So I think if people are still want some clarity on that, can view the previous lecture where I have covered this quantity like more brief. And so since the current critical density of the universe is equivalent to a mass density of rho c comma 0, so this indicates the critical density. There's nothing but the energy density of critical energy density per speed of light square. So it's about 1.4 into 10 to the power 11 times the mass of the sun per mega per second cube. And so once we know this critical density, obviously we can calculate the one of the most important parameters that one has to understand in order to understand how the universe sort of how the universe is and how it behaves and how it will be. So that is determined by the density parameter. So even this I have covered in the previous talks, and so you can get a better outlook in that. So the density parameter of the star is about it's given by the density, the mass density of the star per mass density, critical mass density of the universe. So that approximates about 5 to 10 to the power 8 by 1.4 into 10 to the power 11, and that's about 0.004. And so this is in the case of stars, and but we know that but as you can see that star make up less than 0.5% of the density that is necessary to flatten the universe. So as we have seen before, the when the density parameter of the universe reaches to an exact value of unity or unity. So at that time we can consider that there is no expansion or no further contraction that is going to occur, and so the universe is it's considered to be flat at that condition. And if the density parameter is less than 1, it is said that it will expand endlessly forever. And then if the density parameter is greater than 1, that means it is going to come, contract, and it will collapse at a certain point. So for stars make up less than 0.5% of the density that is necessary to flatten the universe, or in other words, it makes up 0.5% of the density necessary to get the value of the density parameter to be 1. So again, since this has to do a lot, this value which we got here, 0.004, it is also like it can't even have a approximate symbol because it's not so even that precise, as we have considered a lot of, we have made a lot of assumptions that homogeneity is required at such a distance, and then we are considering we are getting a general mass density value. So it is not precisely determined one, and thus largely because the uncertainty in number of low mass and low luminosity stars in the galaxy. So when we are observing, so like we deal with say with stars that have enough energy to sustain nuclear fusion in. But what about like the stars that are like the neutron stars or the blue dwarfs and other stars like that, which have really high mass density but do not have enough energy to sustain nuclear fusion in them, and thus since it does not emit a lot of electromagnetic radiation, it is really hard to detect them, or it is not easy, they are unable to detect at all. So since they have a really great density because they are smaller in size and have a lot of mass within them. So this number, it doesn't really it doesn't make sense to consider this number to be precise, as we still haven't counted for those low mass or low luminosity stars in the galaxies. So sorry. So again, in numerically in our galaxy, for instance, about 95% of the stellar luminosity comes from stars that are more luminous than this. But 80% of the stars stellar mass comes from stars that are less luminous than the sun. And yeah, so the density parameter in stars will be further increased if you include the category of stars, stellar remnants or star remnants. That is after a death of a star. What happens after the death of a star? So it results in those blue dwarfs or neutron stars or brown dwarfs. So as you can see, a brown dwarf is a self-gravitating ball of gas which is too low in mass to sustain nuclear fusion in its interior. So it comes under the criteria in which I had explained before, as such that it doesn't have enough elements, or it doesn't have enough energy to sustain nuclear fusion in it. So because brown dwarfs are isolated cool star remnants and are difficult to detect, so their number density is not well known. But they too are present large in number, such that we cannot completely ignore them, because they too have considerable density mass density, as we can see. So we have to consider even this in our calculation for the density parameter of stars in the galaxy or in the universe. And okay, one second. And so um, and like what we can also see here is that we are also calculating the density parameter for the baryonic matter that is present. So baryonic matter is comes are the matter that are either bosons. I mean, sorry, that are either leptons or bosons. So these two fall under the baryonic content of the universe. So we have electrons, protons, neutrons, and so on. So, but what about the non-baryonic matter? So that is what we will be looking more into more detail in the next section of the talk. And so this is the correct to the best limits that we have. We can calculate the number density or density parameter for baryonic matter that is present in our. So if that is even the current density parameter for the baryonic matter is calculated by understanding or by through the data that is given that they have acquired from what is it? Excuse me. It's called primordial nucleosynthesis. So primordial nucleosynthesis is a phenomena where the lowest isotope of the element is never formed in this process. So nucleosynthesis is nothing but the generation of nucleons. So if we have so primordial nucleosynthesis just directly results to deuterium, lithium, beryllium, and so on, but will never result in hydrogen, helium. So that is about the primordial nucleosynthesis. So only the data that we have acquired from the process of primordial nucleosynthesis is gives us a sort of a closer value to the actual density parameter of the stars in the universe. So that results for about 0.04 plus or minus 0.01. That's about an order of magnitude greater than what we had actually calculated. And so yes. So what you're seeing mostly in the sky are basically just a lot of only the baryonic matter that are present in the universe rather than the stars themselves. So that is about the observable matter in the case of stars. And okay, yeah. So this is what I had hinted on in the previous previously. So galaxies contain baryonic matter, which are also not again in the form of stars, stellar remnants, or brown dwarfs. So there we also have a sort of interstellar medium that is, say, between a star and another star. We have a medium that is an interstellar medium that is present between two objects that are large enough to observe. So the interstellar medium contains a significant amount of gas, and these gases also contain a lot of baryonic matter in. So say in our galaxy in M31, M31 is the our neighboring galaxy, also called as the Andromeda galaxy. So the mass of interstellar gas is roughly equal to 10% of the mass of stars. So that's so they while by looking at this ratio, we can know that that they are not negligible enough to completely not take them into account, and they do contribute to the mass density of the matter that is present in the universe or the galaxy in this case. So in irregular galaxies such as Magellanic Clouds. So Magellanic Clouds are nothing but the lump of interstellar gas that is present in irregular galaxies. Like they are not completely an irregular galaxy, but they are components that are present which result from an irregular galaxy or nearing an irregular galaxy. So the ratio of ratio of gas to stars is even higher. As in irregular galaxy, it doesn't have a proper shape or it doesn't have a proper set of features that we call the galaxy features that we have. So it also contains a lot of baryonic matter. So as you can see, the ratio of gas to stars is even higher. So in irregular galaxy, you have more amount of these interstellar gas medium or interstellar medium rather than the stars that are present. So there is a significant amount of gas between galaxies. So the famous coma cluster contains up to thousands of galaxies. A cluster is nothing but a mixture of a lot, like a portion which contains a lot of galaxies. And there's some luminosity in B band. Since throughout this whole this whole talk, we will be considering of the luminosity that is being observed from the B band because that we need to constrain ourselves to one part to get up to a better conclusion rather than just approximating for all the electromagnetic spectrum. So for the coma cluster, the B band luminosity comes for about 8.8 into 10 to the power 12 times the luminosity of our what is it, our uh, sun. So if the mass to light ratio of the stars in the coma cluster, so that again we have the average value of mass to luminosity ratio. That's about 4 times the mass to luminosity ratio of our sun. And then the total mass of stars in the coma cluster. Again, so because this from this ratio we can calculate the mass up to a greater greater precision. So we use this mass to luminosity ratio. So from this and we substitute this, we get up to about we multiply so that we get up to 3 to 10 to the power 13 times the solar mass. So although 30 trillion star masses represent like they are a lot of stars, but it is still considered to be really small when compared to the amount of intercluster gases that are present between the galaxy and the cluster. So even these account to a lot of the mass density that is present in our universe. So this is something we cannot readily see, or people don't. It is also essential to consider them. And when there was also a report where they had taken an X-ray for only the stars. They have only taken the readings or the luminosity for the stars. But then when they had passed the X-rays to get all the data of the interstellar medium or the intercluster gases between galaxies, they found that its value of luminosity and mass was way higher than the sum of all the luminosity of all the stars, luminosity and mass of all the stars combined in the coma cluster. So even these account a lot in the baryonic, mass and luminosity that is present in universe. So yeah, okay, it was here. So yeah, so the baryonic, the density parameter for baryonic mass and baryonic matter comes to about 0.04 plus or minus 0.01. So it is an order magnitude it's a magnitude greater than the density parameter for stars. So we can see that more than the stars, even these intracluster gas medium also contains a lot of also contributes a lot in terms of mass and in luminosity. So this is about the visible matter. So now that we have gotten a general outlook as to how the mass by luminosity ratio and the density parameter for the observables in the readily observable objects in the universe. So now let's go into computing the amount of dark matter, or why people have even bothered to look at dark matter. So why people give a lot of importance to this. So we'll just have a small outlook at that. And so yeah, this is readily known after means not at the time when they had discovered dark matter, but it was also calculated that up 70% of the universe is dark energy, and up to 26% or 25.4% of the universe is made up of dark matter, and up to 4.1 or 4.2% is made up of the baryonic matter that is present in the universe. So again, I have uh, explained before, like the universe also contains non-baryonic matter, which doesn't absorb, emit, or scatter light of any wavelengths. So this makes these non-baryonic matter to very hard to detect, and since and we know that to understand the properties of say a star or a galaxy, we tend to determine using parameters like redshifts and then the spectral line classifications and so on to understand the general characteristics of the objects. But since the non-baryonic dark matter, it doesn't absorb, emit, or scatter light of any wavelength, so it is really hard to detect them. And so one way of detecting dark matter is to look for its gravitational influence on visible matter. So since space, mass tells the space how to curve, and then space tells mass how to travel. So that's the famous for Einstein. So since we cannot observe it directly, we look at its gravitational influence on the observables present in the universe. So one again, we take an example of Milky Way and M31 again, since it's of a less distance from where we are, and we can get a reasonably accurate data in this distance scale. So a classic method of detecting dark matter. So it can be detected, or can be sort of observed. Its effects can be my correction. Its effects can be observed by looking at the orbital speeds of stars in spiral galaxies. So we have taken an example of our own galaxy, that's the Milky Way, and the M31, that's our neighboring galaxy. So if the radius of the orbit is r and the orbital speed is v, then the acceleration that the star experiences is given by v squared by r. So and then which is directed towards the center of the galaxy. And then if we try to equate it with the Newton's gravitational law formula, so the acceleration provided by the gravitational attraction of the galaxy is given by, so we have ma is equal to gm by r square. So this m and this m gets cancelled. So we have a is equals to gm. So the mass here, this is not like a multiplication. So m of r, m as a function of r, because we are looking at the amount of matter content that is present at a certain distance. So it is not like the overall mass, but it's only up to a certain distance. So we specify this as m of r. So gm by r square. And then equating equation 7 and 8, we get v square by r is equals to gm by r square. And so this is about this. And then the surface brightness of the disk of a spiral galaxy. So basically, before we get into this, there is one important aspect that one has to keep in mind. So when we look at a galaxy, say from like when we are observing a galaxy from Earth via a telescope or any other device. So we look at the galaxies that say we are considering a spiral galaxy. Or spiral galaxy, when we are observing a spiral galaxy, we are looking at it from a certain angle from the position we are present in, from the position we are present. So we look at the galaxy, either the edge-on part of the galaxy or the face-on part of the galaxy. So we have at an intermediate angle. So the luminosity and the amount of matter that we can observe from the galaxy also depends from the angle at which you observe the galaxy. So that angle is represented by, say, oh yeah, this one is, yeah. So say we are observing at a certain angle that is given by the eye. So that's the angle of inclination. And then this galaxy is moving at has a radial velocity of about v. So so we have a formula. I think we are looking. So from the telescopes that we have, we are observing the Andromeda or the M31 galaxy at an angle of 77 degrees. So that is the angle of the M31 galaxy. So when we are observing a galaxy, we need to also look at the angle we also need to consider the angle at which we are observing in order to get the precise data that's coming. So the disk we see in the projection will be elliptical, not circular. So when we have an ellipse, we have the major axis and the minor axis. The major axis given by A, and then the minor axis given by B. So the ratio of B by A is given by cos of I. So the cos of I is nothing but the angle of inclination. And so I'm sorry. So yeah, this is one aspect I wanted to cover before we get into this part also. So the surface brightness of the disk again typically falls off. So it's it exponentially decreases as as the distance increases from the center of the galaxy. So the intensity as a function of the distance or the radius, you can distance from the of observation. So it is I naught times e power minus r by rs. So rs is nothing but the radius from the center, and then the r is nothing but the radius of the galaxy. Yeah. So once a few scales from the center of the spiral galaxy, the mass becomes essentially constant. So we are again making the what do you say, the assumption, or we are trying to get into a case where after a certain large amount of distance, the mass tends to be homogeneous or generally gets constant after a while. So if all stars contributed, or most of the stars in the galaxy contributed for the mass in the galaxy, so then we can see that the velocity would fall as a function of v is proportional to 1 by r. So this r and this r can cancel. So v is proportional to 1 by r. Sorry, root r. I'm sorry. So this is actually called as Keplerian rotation. This certain case is called as Keplerian rotation. So this is about when Kepler had calculated the radial velocity of, say, the objects or a galaxy, when he considered the mass to be concentrated right at the center. So when you tend to go far away from the center, you would say that the mass is generally typically constant as little mass is present at the edge, like away from the center. So yeah, so so when we try to as we have so when we try to consider the angle of inclination, uh, which accounts to the angle at which we are observing the galaxy. So and then one way to again calculate the distance or the velocity of the galaxy is by looking at its redshift. So when we tend to pass the light and we observe the light that is, observe the radiation that is emitted from the galaxy, it tends to get redshifted as due to expansion of space and so on. So the redshift will be as about c times v of v is equals to c times c times the redshift. Redshift is denoted by z. So then when after making the correction for the radial velocity after the angular correction that we made, so we have v of r v as a function of r to be the velocity of the galaxy plus v of r times sin I. So where v galaxy, the radial velocity of the galaxy as a whole, resulting from expansion of the universe again. So that's the redshift component that we have, and v r is the orbital speed at a distance r from the center of the disk. So v r, if we calculate again, we're calculating this parameter. I'm sorry, I should have been better with my note here. This is v r of r. I'm sorry. So this is v r of r. So we want to calculate this parameter, so we turn this and we send it sin I. So as we can see, we have seen here, cos I is nothing but the b by a. So so we have sin I. Sin I is nothing but root of 1 minus sin theta is 1 minus cos square theta. So 1 minus b square by a square. So that is what we get as the radial velocity of the galaxy. So if we approximate the orbital speed v as a constant with radius, so the mass of the spiral galaxy, including both the luminous and the dark, okay, yeah. So the mass is calculated from the this equation. So the mass comes to about v square by g. That is about 9.6 into 10 to the power 10 times the solar mass. So solar masses, and then v square by 220. So 220 kilometers per second radial galaxy. Of our galaxy. So then times the r by 8.5 kilo per second. So so yeah, using our sun as an example, and we can take L galaxy, or the luminosity of our galaxy comes to about 2.3 times the 10 to the power 10 times the luminosity of our sun in the B spectrum. This is also in the B spectrum. So the mass to light ratio of the galaxy, of our galaxy taken as a whole, there should be the slash here indicating the mass by luminosity ratio. Sorry, yeah, it approximately comes to 50 times the mass of sun, the mass by luminosity ratio of our sun into our halo by 100 kilo per second. So our galaxy, M31 is about 100 kilo per second away from us. So that's about that, and yeah. And one thing, the one aspect that we can see from shows up, say we go up to v is equals to 3. The radius of, the distance at which we are observing, say it's like about 3 times the radius of the galaxy. So we can see like there is not many stars that are present, at the edges of the galaxy or at the ends of the galaxy. So then when we are considering the mass to be constant at that level, so because we have seen here that from the Keplerian rotation. So the velocity, angle, I mean the rotational velocity of the galaxy at the edges will decrease by a factor of 1 by square root of r. So it should decrease. But then what we see is that the stars that are present at the or the that is point where it is 3 times the radius of the galaxy. So we expect the velocity or the orbital velocity of the stars to decrease. So we have seen that we get about 220. I mean, we get about 220, right? We have taken I have told you the value. So, but we can see that instead of decreasing, the velocity actually remains constant. And if you think like when they went again to a further distance, that is r is equals to 4, the distance equal to 4 times the radius of the galaxy. So but then they still observe the same pattern where it tends to remain just constant rather than just decreasing. And uh, when the two scientists who observed this, actually they said that and at that time when they observed this, there wasn't enough you know the setup that was present at that time didn't enable us to view a distance greater than that, as it is very far away. So the two scientists observed, they just said that any person who wants to view at a great distance greater than that is just like out of curiosity you can do. It doesn't actually matter to anything. But then later when they had when two other scientists, I think I'm sorry. Oh yeah, Roberts and Whitehurst, and when they had observed that distance is greater at about 20 times the radius of the galaxy. So when they observed, they still observed that it was just constant, and they were confused as to why this was so. Because as per the the calculations that we have made here, so it has to decrease the velocity, orbital velocity has to decrease by a factor of 1 by square root of r, but it wasn't. And if you think this is this is uh, abnormal in our galaxy at distances greater, say about 75 times the of sorry 25 times times the uh, radius of a galaxy, we see that the velocity actually tends to increase. We see when we have observed 220 near this near the overall velocity, orbital velocity of the galaxy. So, but after you say, go up to a certain distance, like 20 times the radius of the galaxy, we see that the orbital velocity of the stars that are present actually increases. It increases to about 235 kilometers per second, and that boggled scientists who actually observed that. And such people were trying to try to look out for reasons as to why this happened and what was the reason actually. And so for to keep the objects at the very ends of the galaxy together was also due to it's called as a gravitational anchor. So the gravitational anchor was said to be a sort of halo around that portion. So that halo is what is making the objects to stick around to the galaxy, to stick around to the edges of the galaxy rather than being flung away from the universe. I mean, sorry, from flung away from the galaxy. So that thing is actually making the speed or the orbital speed also, greater at certain cases. So this dark halo is what we are, trying to understand and trying to calculate. And so, oh, this was actually for the dark halo. I'm sorry. Yeah. And when so when we try to go greater than to 20 kilo per second, so we can try to understand, get an approximate, because after the point of 20 times greater kilo per second, which I suggested from a galaxy, that the speed actually increases. So we had to say that the halo was about 20 kilo per second from the center of the galaxy. So and then, but when they had again, when the technology had, I mean, with the increase in the rapid increase in the technological aspect, we were able to build better telescopes that measured about 75 kilo per seconds from the center of the galaxy, and people observed that it was still the constant, or rather it was increasing. So the radius of this dark halo, which was the cause for this, had to be over 75 kiloparsec. And then this reading was mind-boggling, and it didn't make perfect sense as because from the Keplerian rotation, which the stars had to follow if there's a uniform mass present at a distance greater than 1 kiloparsec, or say 5 kiloparsec. So this was one of the reasons why dark matter concept was essential to explain sort of like why this was happening. And yeah, excuse me. So when you consider this mass or the mass density which accounted due to this dark halo, it was about 4 times actually the observed mass of the galaxy. So say we had the mass of the galaxy to be 8 into 10 to the power 11 solar masses. But when you tend to account to the halo that was present and which was making the speed orbital velocity after a great distance to be constant rather than decreasing. So when you try to account the mass that was actually the dark halo that was the cause for that, so it was about 4 times greater than the mass of the galaxy. So that was about 3 into 10 to the power 12 solar masses. And the total mass to light ratio accounted to 150 times the mass to luminosity ratio of our sun. So if our galaxy is typically in a dark halo 10 to 40 times more massive than its stellar component, then the density parameter of the galaxy must be 4 times of that. So which we had calculated as 0.04, it must now be 0.16. So this is the density parameter. It's just really high, and so the concept of dark matter was adopted and the name was given to this dark halo, which was the cause for such an absurd phenomena that we had observed, which we had seen. So although like the total density of galaxy is poorly known, given the uncertainty in the extent of the dark halos, it is to be larger than the density of the baryons as such. As we have seen, the baryons was an order of magnitude greater than the density that was previously observed. So now it is greater than the density of the density parameter of baryons. So some part of the dark halos of galaxy are, again, since we are not able to observe them, it comes under the non-baryonic uh, matter that is present. So I would like to end my first part of the lecture for this dark matter concept, and in the second in the upcoming talk, in the upcoming section, I will be covering the concepts of dark matter in clusters, as we will go more deep into more clusters and other clusters and how dark uh, affected the observables or the matter that is present. And then we'll also look at gravitational lensing, and we'll try to finally, by using all of this information that we have gathered about the dark matter, we'll try to understand its actual significance and what it could actually mean. So thank you for your time. Yes.